SwayamPrabha. Digital India. Educated India.
Good morning, everybody. Today we'll start our lectures on convective heat transfer. And in the first lecture, we will discuss on Introduction to Convection-1. Now, let us consider a typical convective cooling situation. Cool gas flows past a warm body. The fluid immediately adjacent to the body forms a thin, slowed down region called boundary layer, and heat is conducted from the solid body to this layer, which sweeps it away and further downstream mixes into the stream. Now, convective heat transfer can broadly be divided in two parts. In one type of convective transport, we can see that convective transport from a surface to fluid in motion relates the surface to fluid temperature difference and velocity of the fluid, while the fluid does not flow through an enclosure. Fluid flows freely without any guidance through an overall enclosure. Now, such flows are external flows. An internal flow is a flow configuration where the flowing fluid is surrounded by confining walls, maybe circular duct, maybe rectangular duct, maybe triangular duct. Now, streams that flow through duct are examples of internal flows. Heat exchangers are basically conglomeration of internal flows of various types. So, we'll just recapitulate some parts of our fluid mechanics knowledge. We'll again repeat Reynolds transport theorem. The rate of change of N for a system equals the sum of change of N inside any arbitrary control volume in continuum and the rate of a flux of N across the control surface. So mathematically, if we write this, it will be dN dt. We know that this is total derivative of N equal to del T, and this is volume integral of eta rho dV. V with a mark is basically volume. And then surface integral of eta into rho v. This v is velocity vector dot dA. dA is the area vector. And N is extensive property, eta is specific property. So this is a general statement of Reynolds transport theorem. And for mass conservation, let us rewrite it. So if we call mass as m for the system, we can write dm dt equal to del del t of volume integral rho dv plus surface integral rho v dot dA. V is vector, dA is vector. Now we can write straight away for a system, mass cannot be created, neither can it be annihilated. So dm dt we transferring to right hand side, writing 0. This integral, the control volume is a fixed space, a fixed volume in space. Its boundary is not changing, and it's an open system. So we can write basically volume integral del rho del t dv, and this surface integral we can convert into a volume integral by applying Gauss divergence theorem. So this becomes divergence of rho v dv equal to 0. Then we can write volume integral del rho del t plus divergence of rho v dv equal to 0. Now the volume cannot be 0, so inside what we write is del rho del t plus divergence of rho v. This is then equal to 0. And from here we can again write del rho del t. If we apply divergence on rho v, we can write divergence of rho v is v dot grad operated over rho plus rho divergence of v equal to 0. Now this part del rho del t, v dot grad, this operator is, v is I u plus j v plus kw, and this nabla operator is I del del x plus j del del y plus k del del w. Dot product of that is basically u del rho del x plus v del rho del y plus w del rho del c if it is in 3 dimension. Then basically this is the convective derivative of rho, this is temporal derivative of rho, so this is total derivative of rho plus rho divergence of v equal to 0. This is general form of continuity equation, mass conservation equation, without invoking steady or unsteady situation or compressible or incompressible flow situation. Now for incompressible flows, density does not change, total derivative of density. So this is a condition. Therefore, for incompressible flow, we can write rho divergence of v equal to 0. And clearly rho cannot be 0. So divergence of v equal to 0. This is the governing equation for continuity for incompressible flows. Doesn't matter flow is steady or unsteady. The continuity equation is given by divergence of v equal to 0. Now we have mentioned in the previous part that compressible flow or incompressible flow. Now let us consider change of volume of a fluid under the action of external flows. We can write pressure is being applied, obviously fluid is flowing, and since pressure is being applied, its volume may change. So the modulus of elasticity is minus del P divided by del V by the original volume. Now, modulus of elasticity for water is 2 into 10 power 6 kilonewton per meter square. E for air is 101 kilonewton per meter square. So we can clearly see air is 20,000 times more compressible than water. Now from mass continuity, we may write V plus del V into rho plus del rho. Because of change of volume, density will also change. So V plus del V into rho plus del rho equal to V into rho. From here, we can write del V by V equal to minus del rho by rho. So then, in the expression for modulus of elasticity, we can write minus del P divided by minus del rho by rho. Or we can write del P divided by del rho by rho. Now we can express then del rho by rho equal to or nearly equal to del P by modulus of elasticity, which can also be written as half rho V square by modulus of elasticity. Change in pressure is proportional to rho V square. V is the velocity. So del rho by rho we can write is proportional to half V square by A square, where A clearly arising out of E by rho. So A is basically root over E by rho, and this is local acoustic speed. So del rho by rho is half m square, where m is Mach number. So considering a maximum relative change in density of 5% as the criterion of an incompressible flow, the upper limit of, so if this is considered to be 5% change in density is allowed, or up to 5% change in density, we can call a flow incompressible flow. Then the upper limit of Mach number from here will be 0.334. So flow of air up to a velocity of 110 meter per second under standard condition can be considered as incompressible flow. So even though we started with the statement that air is 20,000 times more compressible than water, air is definitely compressible substance, but flow of air up to a velocity of 110 meter per second, that means up to a Mach number of 0.3, can be considered as incompressible flow. Now we will consider governing equation for the convective energy transfer, and for that we will derive first energy equation using specific coordinate system. Here we use Cartesian coordinate system, and the fluid is flowing. This is a Cartesian system. This is x direction. Velocity component in this direction given by small u. Velocity component in y direction given by small v. And we are considering a control volume PQRS. This is basically open system, and through this control volume, mass can flow, energy can cross, and we will focus our attention on the control volume and try to get the energy balance accomplished on it. And first we will consider that thermal energy per unit mass is given by lowercase e, small e. Kinetic energy per unit mass is v square by 2, where basically v square equal to u square, velocity in x direction, plus a small v square, velocity in y direction. Now, rate of change of total energy within the control volume, we can write del T of rho E plus v square by 2. This is total energy per unit mass into rho into the volume perpendicular to the plane. Dimension is 1, and dx into dy, then dx into dy into 1 is a volume. So volume into rho, that is the mass, and into the total energy del T, rate of change of total energy within the control volume. Now, rate of mass crossing through PQ, we can very clearly write that rho u into delta y into 1. Rate of mass crossing RS, similarly we will write rho u into dy into 1 plus del x of rho u into delta y into 1, del x of this quantity into dx, since this is dx apart through RS surface. Similarly, rate of energy crossing PQ will be this mass into the total energy, that means E plus v square by 2, and rate of energy crossing RS will be then basically the E plus v square by 2 into rho u plus del x of this total energy into dx and multiplied by then delta y into 1, RS side, so delta y into 1. Now, net convective efflux of energy across the pair of surfaces. So then PQ and RS pair of surfaces, PQ, this much amount of energy is coming in, and through RS this much energy is going out. Then convective efflux is given by del x of E plus v square by 2 into rho u into del x del y. Similarly, we can find the efflux across the faces. So this we across the faces PQ and RS found out. Similarly, we can uh, go for an energy balance between PS and QR pair of surfaces. And then so this is in x direction, and similarly a flux in y direction we will be able to get if we perform energy balance between PS and QR pair of surfaces, and then if we add them together we will get del x of E plus V square by 2 into rho U. This is between PQ and RS pair of surfaces, and del y of E plus V square by 2 into rho V. This is PS and QR pair of surfaces into del x del y to make it for the total volume. Next, we consider diffusive transport of energy. Now, diffusive flux or conduction flux across PQ. Again, let us look at it, PQRS. So, basically, this is given by minus K del T del X. We know Fourier law, basically thermal conductivity into area into del T del X. Conduction flux across RS is minus K del T del X dy plus del X of minus K del T del X into delta X. So this is basically then RS surface, so into delta Y. So net conduction flux in x direction is then minus del X of K del T del X del Y. Similarly, net conduction flux, for this we have calculated between PQ and RS, and again if we perform similar exercise for PS and QR pair of surfaces, we will get del y of K del T del Y del X del Y, and then for the whole volume when we write, we can write minus del X of K del T del X plus del Y of K del T del Y into del X del Y. So total efflux of energy, that means the total convective transport and diffusive transport. We are ignoring here radiative transport. At the outset, I should have mentioned it, but it is understood. We are not considering radiative mode of transport here. So basically, the efflux of energy, we can then write, this is the convective component and this is the diffusive component. We have found out separately, and now we are adding them and we can write it in this way. And in vector notation, if we want to represent it, we can write divergence of rho v plus E plus V square by 2 minus divergence of K grad T into dx dy. So this is basically the efflux of energy through the control surfaces, that is describing the control volume. And also we have found out the rate of change of energy within the control volume. So we have found out rate of change of energy within the control volume and efflux of energy through the control surface. That means if we reconsider Reynolds transport theorem, we can say rate of change of energy for a system is rate of change of energy in the control volume. This is time rate of change of energy, which is given by equation 1.16, and then plus rate of efflux of energy through the control surface. 1.24 or 1.25 is basically rate of efflux of energy through control surface. So these two components we have found out, which will basically give us rate of change of energy for the system. Also, we know, according to first law of thermodynamics, rate of energy production within a control volume plus rate of work done on the control volume is rate of change of energy for the system. So here, when we state Reynolds transport theorem, entire right hand side is known, but left hand side is not known. Now, when we write first law of thermodynamics, we can see this statement. And in this statement, if we can calculate rate of change of energy production in the control volume and rate of work done on the control volume, then we will be able to equate that with rate of change of energy for the system. And that rate of change of energy for the system can be equated with right hand side of this Reynolds transport theorem. And that completes our task. So right hand side we have found out of Reynolds transport theorem. Left hand side we are finding out or calculating through rate of energy production within the control volume and rate of work done on the control volume. So let us evaluate the quantity rate of work done on the control volume first. Now, rate at which body force F does work is given by force time velocity. So body force, if that is given by I Fx plus J Fy, then the work done by the body force is rho Fx into U plus Fy into V into dx dy. So we can write rho F vector, which is I Fx plus J Fy, and dot V, that is also vector, that is I into U plus J into V for two-dimensional case, into del X del Y. So this is basically the rate at which body force does work on the control volume. Now we will again look at the control volume and look at the normal forces and the shear forces on each surface. Like here's sigma x, tau xy, here sigma y, sigma xx, tau xy, sigma xx, sigma yy, tau yx. This is sigma xx plus del x of sigma xx into delta x. This is tau xy plus del x of tau xy into delta x. This is tau yx plus del y into tau yx into delta y. So we have identified the basically the surface forces, the normal components, and the normal stresses, and the shear stress component of surface forces. So work done by the surface force on PQ plane of CV. This is minus sigma xx into u into delta y minus tau xy into v into delta y. This is very clear from here. Minus sigma xx into u and minus tau xy into v on acting on the surface delta y into 1. So work done by the surface forces on RS plane, then RS plane this is the normal stress on this surface and this is the shear stress on this surface. So this normal stress into then u component of velocity on this surface, it is working. Shear stress into v component of velocity on this surface, it is working. So sigma xx into u plus del x of sigma xx u into delta x plus tau xy into v plus del x of tau xy into v into delta x, entire quantity into delta y. So net work done will be algebraic sum of these two, and then we will get del x of sigma xx into u plus del x of tau xy into v into delta x delta y. This is again, we can see these two pair of surfaces PQ and RS. Similarly, we consider the forces on these two surfaces, that means PS and QR, and then we will get two additional terms, that means del y into sigma yy into v plus del y into tau yx into u, and we add them with what we got here as equation 1.29, and we get del x of sigma xx into u plus del y sigma yy into v plus del x into tau xy into v plus del y of tau yx into u, entire quantity into delta x delta y. We assume the sources of heat. So this is basically that means what we can say, that we have found out rate of work done on the control volume, and then we have to calculate rate of energy production. And if there is a volumetric heat source S dot TH, the energy production within the control volume S dot TH dx dy. So we have now all the components. That means we came to know about rate of change of energy in the control volume, and rate of efflux of energy through the control surface. Through this is efflux of energy through the control surface. This is rate of change of energy in the control volume. So 1.6 and 1.25, these two will give these two components. And now we have found out rate of work done on the control volume and rate of energy production within the control volume. So basically, if we add them together, that is rate of change of energy for the system. And these two, if we add together, that is rate of change of energy for the system. So these these two quantities and these two quantities we can directly equate now, and that is what we are doing. So after having come to this level, that means the energy generation within the control volume, this is work done by the surface forces, and this is work done by the body forces. So with these three components, we can write the entire right hand side work done by body force, work done by surface force, and rate of change of energy generation within the control volume. And left hand side, the rate of change of energy within the control volume and rate of efflux of energy through the control volume in convective mode and diffusive mode. So this 1.31, this is actually the complete accountability of energy. But we want to know basically the energy equation governing the thermal energy. So for that, we have to subtract mechanical energy from this. And in order to find out mechanical energy, what we do, we multiply x component of momentum equation by u and y component of momentum equation. We multiply x momentum equation by u and y momentum equation by v and then add them up. So we get this equation. I'm not doing it in term by term manner. You can easily understand it, or you can write down the full Navier-Stokes equations in 2 dimensions in x and y momentum equations, x and y components. Multiply x momentum equation by u and y momentum equation by v and add them. You will get this equation, which is rho del del t of v square by 2. This comes from the temporal term. Then u square del u del x, uv del u del y, uv del v del x plus v square del v del y. Again, right hand side, body force, terms arising out of body force multiplied by the velocity components, and this is the basically the surface forces. That means the normal stress and shear stress multiplied by the areas and then multiplied by the velocities. We'll get this term on the right hand side. Now if we look at equation 3.1, which is basically energy equation, considering the thermal energy and the mechanical energy both, we will be able to get this equation, but we require to simplify. So what we have done first we have these two terms, two convective terms, del del xy into rho u e plus v square by 2 and del del y into rho v e plus v square by 2. We have taken up these two terms and then term by term we have simplified. For example, here we have written rho u into del e del x plus e into del del x of rho u, then plus v square by 2 into del del x of rho u plus rho u into del del x of v square by 2. So these first 4 terms are from this. Similarly, then we can write rho v into del rho del y, rho v into del e del y, then e into del rho del v, v square by 2 into del del y of rho v, and then rho v into del del y of v square by 2. Simply expanded to convective terms and also expanded the temporal term. Simply, del del t of rho into e plus v square by 2 we have done term by term expansion. That means rho into del E del T plus E into del rho del T plus rho into del T of V square by 2 plus V square by 2 into del rho del T. Then these terms, that means 1, 2, 3, 4, and these terms, 8 terms, 1, 2, 3, 4, 5, 6, 7, 8. These terms we have assembled together. First three terms we have written also, first three terms of this term, and this term of equation 1.31, and this we have rearranged it after assembling them together, and we can write rho del T of V square by 2 plus U square del U del X uv del U del Y uv del V del X plus V square del V del Y. So this is just all those I mentioned about, all these terms. If we do a little bit of rearranging and do simple algebra, we can regroup them as these terms plus rho into del E del T. This is internal energy or thermal energy. Rho E del E del T plus U del E del X plus V del E del Y. These three terms we get here. So this becomes basically what all we did. We rearranged first three terms of complete total energy equation. First three terms we collect and rearrange them in this way. Now together with this, so if we add diffusive transport term and the right hand side, again let us have a look. These are the first three terms, then the diffusive components, and then entire right hand side. So we now can write from 1.35 is basically describing first three terms. So rho del E del T plus U del E del X plus V del E del Y plus this and all these terms plus diffusive terms equal to entire right hand side. And that is our, again, the complete energy equation, where we have accountability of thermal energy and mechanical energy both. Now this term, if we recall, in between we evaluated equation 1.32, which is basically the mechanical energy equation. So, and mechanical energy equation, how did we find it? We found it by multiplying x momentum equation by u, y momentum equation by v, and then adding up. So this was the mechanical energy equation. Now this mechanical energy equation, if we subtract from this equation, which is the complete energy equation, then we'll get thermal energy equation. And let us look at mechanical energy equation part. So these terms, if we can subtract from these terms, we will see many of these terms will get cancelled out. And finally, so that means from 1.36 we are subtracting 1.32, and if we do that, we will get rho del E del T plus U del E del X plus V del E del Y. This is internal energy. E del E del T plus U del E del x plus v del e del y plus k del 2t del x2 plus del 2t del y2. And right hand side we will be left with, after mechanical energy part is subtracted, we will be left with sigma xx into del u del x plus tau xy into del v del x plus tau yy into del v del y plus tau yx into del u del y. And this energy generation, volumetric energy generation term, volumetric heat source will be there. Now let us, so this is basically, now we can call it equation for thermal energy, or total thermal energy balance can be obtained by this equation. But we want to get them in little more convenient form so that we can apply them on a problem of interest. So there are quite a few steps now. So what we have to do, the terms within the second bracket we will write separately. Del u del x sigma xx. What is sigma x? Basically normal stress given by minus p plus twice mu del u del x minus 2/3 mu into del u del x plus del v del y. So we are not invoking incompressible flow simplification here. We are writing general expression for the normal stress into del u del x, and then minus p del u del x plus twice mu del u del x square minus 2/3 mu del u del x square again minus 2/3 mu del u del x into del v del y. Then we take up this term del v del y into sigma y by. So sorry, we have taken first this term and then we are taking this term. So del v del y into sigma y equal to minus, so sigma y again normal stress in y direction. So minus p plus twice mu del v del y minus 2/3 mu into del u del x plus del v del y. We are not writing del v del x plus del u del y. We are not setting this equal to 0, not invoking the continuity equation for incompressible flows. If needed, we'll do that, but we have remained fairly general. Compressible or incompressible doesn't matter. We are writing for general situation. So into del v del y. So again we multiply term by term with del v del y and get this equation. Remaining terms are these two terms, tau xy del v del x into tau yx into del u del y. So tau xy into del v del x, tau is mu del v del x plus del u del y into del v del x. We get this term, and tau yx into del u del y is mu again del v del x plus del u del y into del u del y. We get mu del u del y square plus mu del v del x into del u del y. So we can then, what we can do, all these bracketed terms we have got their expansion, we have expanded them and we put them together. If we put them together, we can write basically left hand side we do not change, equation 1.37. Left hand side we have written same, rho del E del T plus U del E del X plus V del E del Y equal to K del 2T del X2 plus del 2T del Y2 diffusive terms minus, so from these we can see these four terms and This 1 2 3 4 1 2 3 4. So these 12 terms we rearrange and we can write minus p del u del x plus del v del y plus mu into this minus p del u del x and del v del y we collect from here. These two terms do not have viscosity component, are not multiplied by viscosity. All other terms we have viscosity as a multiplication factor. So we put them together. We can write mu twice del u del x square plus del v del y square plus del u del y plus del v del x whole square minus 2/3 del u del x plus del v del y square. Now this is del u del x plus del v del y. Del u del x plus del v del y, if we set equal to 0, that will then it will be simplification for the incompressible flows. But as I said, that we have remained general so far, not invoke the condition for incompressibility. So then this is the complete viscous dissipation, and it is mu into uppercase phi, and uppercase phi is given by this expression which is called viscous dissipation function, and that into mu is complete viscous dissipation plus S dot th thermal heat source. Now equation 1.42 is a general form of energy equation valid for both the compressible and incompressible flows. Now let us consider enthalpy per unit mass. It is given by I equal to E plus P by rho. It is a very known terms in thermodynamics, but in thermodynamics course you have written this as H equal to U plus PV. Here only the symbols are changed because in heat transfer we do not use H as enthalpy, because H is reserved here for convective heat transfer coefficient. So I is enthalpy, and instead of thermal energy or internal energy in thermodynamics we usually use U. Here we have used E. Consistently so far we have used, and you have read H equal to U plus PV. H is enthalpy equal to internal energy plus pressure P and the specific volume lowercase v. So here, because v is for velocity, so we are changing all those things as I is the enthalpy equal to E internal energy plus P by rho. Rho is the density, so 1 by rho is the specific volume, P by rho. And now what we do, we substitute E by I. That means every E will be replaced by I minus P by rho. Every E will be replaced by I minus P by rho. Now this is del del T of E, so this will be E will be replaced by I minus P by rho. And so what we have done, that rho del I del T plus U del I del X plus V del I del Y, and of this del del T of minus P by rho, U del del X of minus P by rho, and V del del Y of minus P by rho we have transferred to the right hand side. Not yet transferred, we have separated, written them separately. So we have written minus rho del del T of, as I said, minus sign is common, P by rho plus U del del X of minus P by rho and V del del Y of P by rho. We have just separately written them, equal to then K grad square T minus P del U del X plus del V del Y. We have written as such everything just what we wrote here, plus mu into viscous dissipation plus thermal energy generation rate. So now we just perform these calculations, keeping these three terms on the left hand side intact, minus just again we have performed the derivative operation once on P, then on 1 by rho. Here also del del X once on P, then del del X on 1 by rho, del del Y of P on P, and del del Y on 1 by rho. And we have got these terms. Right hand side K del square T minus P del U del X plus del V del Y plus mu into viscous dissipation plus thermal energy generation rate. So now we write rho del I del T U del I del X plus V del I del Y equal to K grad square T, and then transfer all these terms on the right hand side and rearrange them. And in the right hand side, then we can write basically del P del T has come to right hand side. We are bringing it here, and we are also U del P del X and V del P del Y. These three terms we put together, and this becomes total derivative of pressure. We can write them as del P del T plus V dot grad operated over P. So this term is taken care of, and this term, and this term are put together here. Then remaining all the terms from here, that means basically this term, and these two terms are rearranged in this way. Then mu into phi plus thermal energy generation. So again rho del I del T U del I del X plus V del I del Y equal to K grad square T, and this is, we can write total derivative of pressure dP dt, and these terms can be again rearranged as minus P by rho del T plus, here basically these two terms together will be del del X of rho U, and these two terms together will be del del Y of rho V, plus mu into phi plus S dot TH thermal energy generation rate. So we can now write rho del I del T plus these two terms we can write convective derivative of I, basically V dot grad operated over I equal to K square T, K del square T plus dP dt plus mu phi plus S dot TH, because here this is the general form of energy equation. Even though we have not invoked this is general form of continuity equation, and we have not invoked continuity equation for incompressible flows and kept it fairly general, but this is del rho del T plus del del X of rho U plus del del Y of rho V. That means del rho del T plus V dot grad operated over rho. So this is total derivative of rho d. So this we can general form of continuity equation. So this is del rho del T plus del del X of rho U plus del del Y of rho V. So basically del rho del T plus this convective derivative of rho plus rho into divergence of V, that means del U del T plus del U del X plus del V del Y. So all the terms we can get here. Del rho del T, this will give us rho del U del X plus U del rho del X. This will give rho del V del Y plus V del rho del Y. So total derivative of rho plus rho into divergence of V. All the terms are here. Basically, this is the complete continuity equation without considering compressible flow or incompressible flow. So this can be set equal to 0. That is how this total term is dropped, and we can write K grad square T plus dP dt plus mu into phi plus S dot th, and left hand side is rho di dt plus B dot grad operated over I. So this is basically total derivative of I. So rho di dt equal to K grad square T plus dP dt plus mu into phi plus S dot th. Let me repeat again that equation 1.46, what we can see, we can come here. Only we have to pay attention to this part. Here, this is the complete continuity equation. Del rho del T plus del del X of rho U and del del Y of rho V. So, irrespective of compressible or incompressible flow, this is the complete continuity equation. So we can drop this is 0, we can drop this term and we come here. Equation 1.48. Now in this equation, if we substitute I, that is enthalpy, equal to Cp into T, we can write rho Cp. We can very clearly write rho is here, I is Cp into T. So we can write rho Cp into d temperature, d time, total derivative of temperature, equal to, we had dP dt. So total derivative of pressure plus K grad square T plus mu into phi. This phi is basically the viscous dissipation factor. This is total viscous dissipation into thermal energy generation. This is a general form of energy equation. Now in 2D or 3D, you can expand it according to your requirement. Now what we will say, this is the general form of energy equation, but if we want to write it for liquids, we can from here also we can write from general equation, but very easily we can take recourse to equation 1.42. Just let us go there. Equation 1.42, we can write internal energy equal to Cv into T. So left hand side, E is substituted by Cv into T. Right hand side, this term will be there. If we for liquid, that means we are invoking the conditions for incompressible flow. This will be 0. So this will be dropped. Here this will be Cv into T, and in the viscous dissipation also this will be dropped. So viscous dissipation term for compressible flow and incompressible flow are different. This is the complete viscous dissipation term. If we invoke continuity equation for incompressible flows, we can drop this. So this will be then viscous dissipation for incompressible flows. This term will be dropped, plus thermal energy generation. So let us see whether, if we do this, we can get this. So we can get rho into C dt dt. We have written deliberately C. C is CV, we have written here. And then K del to T del x2 del to T del y2 plus, and in equation 4.2, this P, this is dropped. So this term is completely dropped, and mu into phi, viscous dissipation. But meaning of viscous dissipation for incompressible flow is slightly different, because this term will not be there. Only these terms will be there. For compressible flow, viscous dissipation is this term and extension of this in 3 dimension is also straightforward. In 3-dimensional compressible flows, this term will be del u del x plus del v del y plus del w del z square. But again, in 3-dimensional for incompressible flow, this term will be dropped. Continuity equation. So this is the viscous dissipation plus thermal energy generation. For liquids, Cp equal to Cv equal to C, and P del u del x plus del v del y is 0. So in the case of liquids, the viscous dissipation term will have to be modified by invoking incompressibility condition. So this is then and rho dt d temperature. That means this is basically del T d temperature d time, total derivative of temperature. So that means this is del T del of temperature plus u del T del x plus v del T del y in 3-dimension w del T del z. And this is k del to T del x2 del to T del y2 in 3-dimensional cases del to T del z2. Mu into viscous dissipation into thermal energy generation. For liquids, the interpretation of this equation we have discussed. And for liquids or gases, when we want to be independent of compressible or incompressible flows, we can use this. Specifically for gases, we have to use this, which is rho Cp, again total derivative of temperature, equal to dP, total derivative of pressure, plus K rad square T plus mu into viscous dissipation plus thermal energy generation. So we have derived the energy equation for gases and liquids for compressible and incompressible flows, and now we will apply them depending on the situation, the flow configuration, and the flow condition, whether it is compressible flow or incompressible. We will stop here today. Thank you very much. Thank you for your interest. Thank you.